we are going to talk a little bit about some of the things that we've done in the United States during the shale gas development. Some of this, of course, applies to shale oil development as well. And some of the lessons that we've learned, some of the things that we've changed along the way to improve how we do things and how to minimize our environmental footprint, and how hopefully, if or when you develop shale gas in the UK, how some of these things can be applied here to try to potentially have a smoother path in some of these regards. These are some of the headlines that we've seen in North America for the past several years. Some of them have been more intense at certain times. Some of those headlines apply specifically to specific problems that have been more intense in certain regions of North America, and some of this, of course, applies already in the continental Europe. Discussions are ongoing, things that you see in media. And so when we look at this as an industry, or of course as a consumer, we got to consider about what are these coming from? Where do they originate from? What can we do to try to prevent these and work around these? And what can we do as an industry as a whole to make sure that people don't have to be concerned about these things and that we are developing our resources responsibly? What I'll talk about, it's a 20-minute presentation, so it'll be rather brief, but I'll be available to discuss with any of you afterward the session. Some of the highlights on how we as an industry can try to help provide assurances, be open, inform what we're doing, so that people actually learn about the technology that we're doing and understand why we're doing certain things. One of the things in North America we may not necessarily have been very good at is communicating. Making sure that we have the information available. Some of these aspects have been brought up already in the discussions this morning. We'll talk a little bit more about that. For example, disclosure and how it took a while before that happened in the United States. But also how we can strive for environmental leadership continuously. So not just try to assess the concerns that are immediate, but also try to continuously develop better products, better technologies that are more environmentally responsible to help minimize the environmental footprint associated with this process. So one of the things that we talked about a little bit earlier today is groundwater and groundwater contamination concerns. And I have several people here in the audience that are from Halliburton as well, Pinnacle, that have more experience on this specifically. But we have data available where we can look at where are the groundwater supplies. And so this has been done. This is just one specific example. You can see the blue here on top is where your groundwaters are, and here on the y-axis you have the depth in feet. And the distances where you have those as compared to where we have our mapped frac treatments. So this particular one is in the Marcellus, which is in the northeast of America, but we also have done this on other regions in the United States, and you'll see similar trends that generally speaking you have a distance, a delta here between where the frac treatments are and the groundwater treatment of up to several thousand feet. And these are data we have available. It's just something that hasn't necessarily been shared early on as we discuss these. There are several papers associated with this, and I can provide references if you guys want them later. But another thing about the whole thing, disclosure, chemicals. So we use chemicals during our hydraulic fracturing treatment. And when we use chemicals, most people in our industry are not chemists. I'm a PhD chemist. But most people don't have the background necessarily related to chemicals, what they're used for, what contains what's in them, which ones are dangerous, which ones are not dangerous. So one of the things that the industry eventually did was start providing information related to this. So there's one website, several of you may have heard of fracfocus.org, for example, where you can find some of this information. A lot of the companies have their own internal websites, and this is an example that I have here, where you can see, you can go to the map, and this is a continuously expanding effort, but you can go to the world map, and we started this effort in North America, because that's where we did a lot of the shale gas and shale oil development, unconventional development. And you can look at the states. So if you're in Pennsylvania, the specific example is in Pennsylvania, we have X number of fracturing fluid formulations there, and you can click specifically on the one you'd like to know more information about. And it will come up a sheet here where it lists the additives that are part of that formulation. It can also give you a pie chart of how much of each one of those as a relative percentage to everything else that's in that fluid do you have with that specific component. And it also lists the specific constituents that's part of that fracturing fluid. So for example, if you have friction reducer, gelling agent, biocide, and so forth, you can get the information, what they are, why are we using them, what's the purpose of them, what are some of the common uses that they're used in other types of industry for that specific chemical, and then also list within each one of those, because each one of those components can have specific chemicals in them. So you can get all this information here. And like I said, this is a continuous process, and this is something that's only been in the works for a few years. But obviously, as you move towards potential development in continental Europe, this is certainly something that's probably on the top of the list of things to get done and make sure that it's actually disclosed to the public so everybody can view it. So hydraulic fracturing is something we do. We've done it for a long time. But yet those headlines that I showed you in the first slide is something that started relatively recently. Obviously, it's with the large expansion of unconventionals, so started a lot more media attention and so forth. But it's really important to make sure to communicate to people what you're doing. So as an industry, we may not have been very good at that in the past, but that's something we need to start talking about. So making things publicly available, like on a website, is one way to do it. Having people go into talk at different venues is another way to do it. But also discuss with people in general, what is a frac fluid, what's in it, and why do we have those things in that fluid. And so one of the things that the industry's been doing is looking at the constituents and try to minimize the type of constituents that you have in there. Are they really necessary? What do they do? That specific constituent, what alternatives do we have within that constituent? So for example, if you're using a biocide, there may be a range of biocides. Now, some of them apply to certain regions for certain requirements, but sometimes we have a choice of going from one to the other. Very often, it's steered by a matter of cost, but sometimes you have a choice. I mean, there may be similar costs, and you maybe have two different chemicals. The information of the disclosure site there, you can get the MSDS sheets, for example, as well, to these chemicals. Some of them may be classified as hazardous, some of them may not be classified as hazardous. A lot of companies in the industry also developing internal scoring indices. So for example, if you are working on either product development or if you're evaluating your current portfolio, you can use it to evaluate it on health, safety, and environmental scores so that you can do the more responsible product in the choice of when you present a proposal to a customer, for example. But mainly what we're looking at is water and sand. Okay, so we can keep saying this, and that's fine. But at the same time, we do have some other chemicals. But it's important to know that, relatively speaking, they're a smaller percentage. And then they have its purposes. We're using them to help carrying the proppant out in the fracture so that we can actually generate production. Striving for environmental leadership. There's several ways we can do this, and I'll share a few examples of some of the things that have been done in North America and how we help apply these. The first one I have there on the left is recycle. So a couple slides ago we talked about the majority of this is water. And yes, we do use large quantities of water. You can discuss relative to other industries whether or not they're really large or not, but the reality is we use large amounts of water. So as we're using this water for the hydraulic fracturing treatment, you also generate a byproduct. So that byproduct is flow back and produce water. So it's also water. When you're generating that byproduct, it would be silly not to consider to try to recycle it. So that's one of the efforts. This discussion started probably about 6, 7, 8 years ago in North America. And there's different reasons for that. There's different drivers. It could be drought, climates, for example, lack of fresh water, or it could be difficulty disposing of these waste products. That could be another driver. But recycling is something that's now much more commonly done in North America. That wasn't really done much many years ago. If we can remove certain things from the fracturing treatment, that's another way that we can try to improve. This specific example, and I'll show a little detail later in the slides, is where we removed a certain chemical component and we've replaced it with another method of implementation. So there's certain things we can do to be better like that. Another thing, specific biocide, for example, that was used. Biocides generally generate a lot of discussion. related to the fact that biocides are intended to kill something, right? They're intended to kill the bugs. Or if it's intended to kill something, then it's got to be really bad. And generally speaking, a lot of biocides are listed on MSDS sheets as hazardous materials. Of course, we use them in rather small amounts, but anything you can do to minimize the amounts of levels of those chemicals that you use, or in certain cases, if you can replace them with mechanical means, those are some of the things that we can do as well, and that we have done. And then as we continuously develop new products, how can we develop things that aren't necessarily classified as being hazardous? How can we come up with things that are safer, or the public would view as much safer than would be traditionally used? And I'll talk a little bit about that. So the recycling, large amounts of water. There's really two water issues. There's one that's a matter of the usage, so that's fresh water, and obtaining fresh water, which in certain parts of North America, and for sure in continental Europe as well, can become an issue to obtain consistently throughout the year and throughout potential drought areas. If there's a matter of who's going to get water, if it goes to general public or development of unconventional resources, it's going to go to the general public, clearly. We all want to have water to shower or to drink and so forth. But if you also have a byproduct that's generated, that traditionally speaking, and we all know fresh water is fresh water, potable water you can drink, it's clean, it's low in salt. But when you talk about the byproducts that's generated, that's coming back, and that can be, up to 40%, roughly speaking, of what you actually put in. That's a large volume of water that could potentially be used, that generally speaking in the past was only considered a waste product. Typically in North America, they would take that water that was continuously coming out from the well, and they would put it in trucks and to go to a disposal site. Depending on where you are located, that's still an option. Some people still do that. But more and more people have started to recycle this water. And so the question becomes, why haven't we recycled it this entire time? Well, the issue with these types of waters has been pretty consistent. The variability of these waters is tremendous. So fresh water, if you pick from a specific fracturing job, let's say you pick it from a pond nearby. Okay, you go 50 miles down the road, you're going to do the same thing. There's another pond, you're picking that water. Those two waters, chemically speaking, will not be completely identical. They'll both be fresh waters. There'll be slight variations in the salt content. Of course, algae and biological things growing in them and so forth will be slightly different as well. But they're both relatively clean, and typically we can get our fraction fluids to work with the constituents in that water to make a sufficient fracturing fluid. Now, the flow back and produced water coming back, on the other hand, then we're really talking variability. So if you have a fresh water, let's say it's 500 milligrams per liter of salt total, these wastewaters, they can be anywhere up to over 300,000 milligrams per liter of salt content. So these can be waters that are essentially brine waters and close to saturation. And when something is close to saturation, if you want to do something with it, you want to recycle it somehow, there's a couple of different methods you can use. One of them is you can say, well, let's try to treat this water. And if so, which method of treatment do we use? These are just a few listed. But the industry has gone in and looked at these various treatments now for the past 7 or so years. And the debates are still ongoing, which treatment is better, which one actually applies to a majority of these waters. Because the issue becomes, when you have variability of source waters, such as these wastewaters, that vary from 20,000 milligrams per liter up to over 300,000 milligrams per liter in salt content. And not just that, individual salts within that mixture from one water to the other varies as well. And if you're in the same area, let's say we talked about Marcellus Shale earlier, let's say you're collecting water only from that area, they're not going to be consistently the same. If you collect it 1 week to the next week to the next week to the next week, they're all going to look different. So if you want to have a robust treatment method, that becomes pretty challenging. And one of the biggest challenges is when you do this treatment, you're going to generate some sort of waste. And one of the things that North America has been rather lucky regarding has been that the actual flowback and produced water has been classified as non-hazardous waste. It's oil and gas exempt. Now that may change. There's a lot of discussions ongoing with that. And certainly in continental Europe, I don't think you'd be in the same situation. But with that said, you wouldn't have had to completely undergo a chemical analysis of the water before you disposed of it. It's a waste, but it was relatively easy to dispose of this waste. Now, if you chemically treat this water or mechanically treat this water somehow and you generate a waste, well, that waste now has to be analyzed and disposed of properly. And as you know, if you know anything about chemistry, as you concentrate things, they get more concentrated, which means if you had high salt content to begin with, maybe there's some potential norm issues related to that water that if they're in the diluted water may not have been a big issue, but as you concentrate them through treatment, that may become a problem. So there's been a lot of discussions about what's actually the best way to do treatment. And there's no silver bullet. There's no bullet that's going to take all of these wastewaters, magically treat them, generate no byproduct, and generate potable water. That's just not how it works. So people have looked at various methods. And what the industry did was they went to the wastewater industry. They looked at how do we clean up our wastewater that you then end up in your sinks again and your reuse and so forth. Well, the salt content isn't the same there. The waste product that's within that water isn't the same. So if you take those and magically try to apply them to these types of wastewaters, the issue becomes that your equipment will foul. The membranes, for example, if you use reverse osmosis, will immediately foul. They're simply not set up to function with these types of wastewaters. So you have high organic content, you have high solids content, you have high dissolved solids content, and that's all a problem when you're looking at treating these waters. So you will have some sort of modified chemistry probably that you're going to do to treat these types of waters as compared to typical municipal waters. And you will get some sort of clean water. Depending on which treatment you used, that clean water could be simply solids-free water, or it can be potable water. Because not all treatment methods generate the same end product either. And if you generate really nice, clean, potable water here, you're going to end up with a large amount of waste. So essentially you taken one waste problem and conformed it into another waste problem. So there's still debate ongoing related to treatment, and there's still a lot of treatment companies, but most people have moved towards doing a minimal type of treatment, which means you're not removing all the salts that's present in this water. I'll give you two examples. If you have a water that's close to saturation, let's say you have a 250,000 TDS, total dissolved solids, produced water. If you put that through a distillation unit, you may end up with, just making up numbers here, 20% of desired product, and the rest will be a byproduct. That doesn't seem very efficient. If you take another water, however, that's much lower in salt content to begin with, and do the same thing, you may end up with a reverse scenario, where you have 20% byproduct and 80% product. So that doesn't sound so bad. But you're on a location where the water source isn't going to be consistent, then you have to consider that if you want to come up with a viable option that makes financial sense. And another thing related to this as well, where are you going to use that water afterwards? So if you're going to reuse it in hydraulic fracturing, the question quickly became, do you need potable water or fresh water in hydraulic fracturing fluids? Traditionally speaking, the answer to that question was yes. Nobody ever thought that it could be done with salt waters. Then some development started years ago where certain areas, Gulf of Mexico, for example, now this is becoming a big problem in Saudi Arabia. There's lack of water. What type of water do they have available? Seawater. So that's something that people are starting to use in fracturing fluids. So seawater, relatively to flow back and produce water and salt content, is relatively low. Depends on which sea you're in. Gulf of Mexico, about 30-something thousand milligrams per liter. The Arabic Gulf, those are a little bit higher. But it was possible. People developed fracturing fluids designed specifically for these waters. There are some challenges associated with it, maybe some more QA/QC type testing that was required. But people have been doing it, and it's been on the market for quite some time. So people slowly started changing their minds about potentially how can we do hydraulic fracturing. Maybe instead of taking these flow back and produce waters, running them through distillation units and using potable water again, at the same time as we're generating large amounts of waste that we still don't really like that we're doing, maybe we can just try to reuse them with minimal treatment as easily as possible. So one of those things is electrocoagulation that's used commonly today in North America. This essentially removes the suspended solids and some of the salts, but you're still left with a brine water. Now, if you do that, you have to come up with better chemistries. So in response to this, and the fact that the industry realized that it's just not feasible to generate potable water out of all this flowback and produced water that we're generating, but maybe we can just try to reuse it with either no treatment or minimal treatment, we definitely have to develop better chemicals. So traditionally speaking, if you run a water frac formulation, you use a friction reducer. You're relying on very high rates to pump that proppant out into the fracture. And as you're relying on those high rates, 100, 120 barrels per minute, these are very high rates, you're increasing surface friction as you're piping this water down through the pipe, which means increased surface horsepower and so forth. The friction reducer is essentially your most important component. But when you take that friction reducer, these are high molecular weight polyacrylamides typically, if you take those friction reducers and put them in the salt waters and try to use them, they don't function anymore. So you can pump them, you can increase the levels, and you can hope for the best. But if you're on location, you're trying to do this, if you're running very salty water and your friction reducer isn't performing, your surface treating pressures are going to go up, and you're going to be left with no choice than to slow down the pumping rate. And if you slow down the pumping rate, and what you depended on to get the proppant on the cracks was the high pumping rate, then you have an issue and people start being concerned with less production. So that's one of the things chemists had to come up with, was better friction reducers. And this one here is just an example. The red line, see on the y-axis, this is percent friction reduction, and you want the number to be as large as possible. Just a comparison between a new friction reducer and a traditional friction reducer in a really high salt water. And if you were to take, for example, this friction reducer that's represented here in the blue curve and run that on the job, you have to slow that job down significantly. You probably wouldn't be able to put away the job successfully. Another example, if we can switch slides, another example is in cross-linked fluids. So now we have a little bit more complex chemistries. So friction reducer chemistries, even though they weren't successful to be used in salt waters previously, was a little bit more straightforward to develop a solution to. However, when you look at cross-linked fluids, now we're talking about having a viscosifying agent, thank you, having a cross-linker, and then having a breaker to make sure that the gel that you're producing, you can break it down before you flow the fluid back. To make sure that all of those work, in these waters that have a variety of contaminants in it, is close to impossible if you use standard recipes. Standard recipes is designed that these individual components that you add to the fluid will work with each other, which is challenging enough. You want to make sure that the breaker doesn't break until it's supposed to break, but you want to make sure the crosslinker crosslinks when it's supposed to crosslink. Now, with all these ions within there, they're either going to potentially delay it, completely shut down that process, or speed it up. So you're not going to have the physical properties of that fraction fluid that you want to. So that's another thing that our scientists have to start working on. And so I'll just show one example here. The yellow line, here you have a freshwater, traditional fraction fluid, one particular fraction fluid recipe. We're measuring the viscosity as we increase the temperature over time. And so in this particular fluid, that yellow profile was how they wanted it to look. If you take that same recipe, however, with a mixture of mostly fresh water still, but some of this produced water, you can see all of a sudden this does not at all look the same, the orange curve here. However, what scientists figured out after many, many months of trying is that it is possible to indeed try to match that viscosity profile curve, even with this water, using the same components, but you have to come up with a customized formulation. So the amounts may be completely different, but it's possible to do in 100% untreated water. So these are pure wastewaters that you can actually do this with. Another thing, removing gelling agents. Guar is typically what we use as our viscosifying agent in our cross-linked fluids. And typically, it's been generated in a slurry in a hydrocarbon carrier. Well, a hydrocarbon carrier, that leads to BTEX. That does not sound good. What can we do about that? So one of the things is we ended up using a mechanical means for hydration to try to make sure that we still have the efficient properties that we needed while removing this hydrocarbon carrier. So there are things we can do and try to combine mechanical means as well as chemical means of remove one where it makes sense. Another thing, ultraviolet light we've used to replace biocides. Care has to be taken when you do this. Certain things don't apply everywhere. These methods aren't effective in all cases. You have to do some pre-job testing, QA, QC testing, to make sure that the water is transparent enough at the 254 nanometers to actually penetrate and be able to kill bugs. But that's one other way where we can actually replace a chemical completely by using UV light. And what we do in here is we have the frac tanks where we keep the water, and our units with UV light in between the frac tanks and the blender, and essentially we treat it on the fly as we go downhole. And then finally, fracturing fluid system, developing new fracturing fluid systems. One team in the research and development area was challenged with coming up with a new fluid system that was much safer. They looked at different lists. Where do we pick these components from? How do we know what's considered safe by the general public? Well, if you eat it, most people consider it safe. So they looked at the Code of Federal Regulations CFR 21, which is a list available for whatever's allowed to be in food additives. The rule was it has to be good performing, it can't be any worse than current fracturing fluids, and you can only pick components from that list. So a team went at it and developed a new fracturing fluid system. Now, this fracturing fluid also, listed the different constituents we have, and of course here, on this particular list, you'll see common uses in all food products, because these are things that are in things you eat. But it can be done. It's just that nobody had thought about doing it before, because we hadn't been challenged to do it. So now, this is part of our product development where we continuously evaluate products to make sure that we do it in a responsible way. And of course, the properties still have to be equivalent or better than previously. So just to summarize, this is my final slide. Some of the things the industry can do, we just haven't done in the past. Not because they have been impossible, but simply because people haven't thought about it as much. People haven't been questioned as much about what they're doing, why they're doing it. Is every single component really necessary? And how do you evaluate the things that you use in your fracturing fluids, for example? So with that, I think we're probably around out of time. And if anybody has any questions, we'll probably try to take them maybe after the session.